Make sure you work through this long question. Pause the video for as long as you need. So Prin's algorithm is finding our minimum spanning tree. So we start with S and we're going to add the node with the shortest weight. So that will be 3. Then we'll add 6, the shortest one that's already connected. The next one up will be G, which is 7. Then we could add H, which is 6. Then F, which is 2. I think 7 is the next one there. Then this lets us add 5. What else can we add? We can add the 8, and then we can add this 8 here. Almost missed that one. And we can then add this one here. Let's just check my solution, make sure I did that right. That doesn't help check it particularly, does it? Well, hopefully it's right. Okay, the conditions that this meets, well, there are certainly no cycles. So stop it. We've met number 1 for this one, and the shortest length of cabling is used from S to every other computer. So this bit here is not correct. Okay, the total cable length for the whole network is the smallest possible length. That's the nature of a minimum spanning tree, but the first bit is not correct. So that bit's okay, that bit's not. So we've only met condition 1. Next, we're going to do a graph using Dijkstra. So let's get rid of all of this. So we start by labeling S with 0 and a distance of 0. Next, from S, we go to D, which will give a temporary label of 3. We go to C. This is going to get pretty messy, isn't it? Which will give a temporary label of 6. And we go to A, which will give a temporary label of 10. We label D as vertex number 1 with a permanent weight of 3. And now from D, we consider neighbors, which lets us go to G, which is 10. We're not going to update C, so now we're looking at 10, 6, and 10. We're going to add C as our second vertex with a permanent weight of 6. Next, from C, we're not going to update A, but we are going to update F. Let's see if I can squish this label in here. So 6 plus 8 is 14. We look at the unlabeled vertices. We have 10, 14, and 10. Let's use G down here. So this is going to be number 3 with a permanent weight of 10. From G, we can update H with 16. We can update J with 18. And that seems to be it. So now we can consider A. So we have 1, 2, 3, number 4 with a permanent weight of 10. And now from A, we can update B to 18. So we go 18 there. That's all we can do. So now what are we looking at? We've got 18, 14, 16, 18. So we're next going to label F as 14. From F, we can update E to 24. H gives us the same weight as we already had, so that's going to stay as 16. B would be 21, so that's worse. Okay, now we're looking at 18, 24, 16, and 18, so H is our next one. Number 6, we label with 16. From there, we're not going to update J because it's bigger. We can update I to 29. And that's it. Next, we've got a couple of 18s that we could use. So let's do this one quite randomly. 6, 7, that's got a label of 18. 18 plus 12 is not less than 29, so we're not going to do that one. Okay, so now we'll do the other 18 as our permanent label. So number 8 with 18. That lets us update E to 23, which is slightly better. Now we are choosing between 23 and 29, so we will label E9 with 23. And from E, 23 plus 9 is 32, so that doesn't help us. So we end up with the 10th vertex being labeled 29. And we check how many vertices should we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, that starts at 0, so that's all fine. Now we need to backtrack. So we'll start at 29, and we're looking for the edge where the difference between, well, we're going to choose H, you should explain it in context, because 29 minus 16 is 13. So I might just change color, do this in green. So we're going to have this edge here. From 16, we're going to go to 14, because that's got a length of 2. We're not going to go to G, because 16, oh, in fact, we could go to G, couldn't we? We could go either to F or we could go to G. And from memory, that's going to create a problem for us later. Just to illustrate a point, I'm going to put this here. But remember that we could have gone either from H to F or H to G. 16 to 10, 16 to 14. Yeah, that's still fine. Okay, we can see, we can work all the way backwards to S first if we like. In fact, let's do that. So now we'll go from G to D, because 10 minus 3 is 7. 3 minus 3 is 0. Now let's look at G. 18 minus 8 is 10. So we've got this one here. Let's go to E. Where are we going to go from E? 23 to 18 is 5. So we're going to have this one. Then we're going to go from 18 to 10, which puts us at A. 10 to 0. That's all good. We can see that from F, we're going to go 14 minus 8 is 6, and 6 minus 6 is 0. So that gives us all of the shortest distances and the path to take those shortest distances. Now, which conditions are satisfied here? We can certainly see there's no cycles. And have we used the total cable length for the smallest network? Was that the smallest possible? Well, going back to our prims tree, which I've forgotten, I'm just going to show you the whole answer slide, so don't. So here you can see, excuse me, we've got our minimum spanning tree here, and then we've got our 2 Dijkstra options, and you can see that there are 2 different options for Dijkstra which happen in that circle. Now the weight of the minimum spanning tree was 61, this one was 74, and this one was 71. I think this one is tricky to realize unless you noticed that there were these 2 different options and that they would produce different solutions, because with option 2 we've necessarily chosen the one with the smallest possible length, whereas with option 1 there was a small one which was option 2, so that wouldn't count. And you can see the answer there in blue, how we could have modified Dijkstra to make sure that we always do that. So we're always choosing the one with the least weight edge leading into it. So here we are back to, we imagine we're at H and we're deciding, do we add HF or do we add HG? And what we're saying is that we should have added HF because it's going to obey all the rules of Dijkstra. We're just adding a smaller edge leading into it. So we should have added this one here. I think that's pretty hard to see. My initial thought was it got something to do with the minimum spanning tree, because it talks about the total cable length for the whole network is the smallest possible but that's while we've used the shortest length of cabling to every other possible computer. So that condition wasn't satisfied with the minimum spanning tree, because although we've used a small amount, the smallest amount of cable in order to connect everything, it's not the smallest amount, it's not the smallest path. So to get from, for example, S to I is going to be a much longer path than it would have been to go via the minimum spanning tree. Okay, yeah, it's quite tricky, but we can get most of the marks there, certainly, by just working through our algorithms and watching out that we don't make any mistakes.